On July 1, 2025, the night sky over Chile's Atacama Desert was crystal clear. Perched atop 0.1, the Atlas telescope was conducting its routine sky survey. Its automated system captured data on thousands of celestial objects every second. At 3:17 a.m., a faint moving point of light triggered an internal alert. This object, temporarily designated A25X Joan, had a brightness of approximately magnitude 20. Its velocity and angular motion differed markedly from typical asteroids or comets. Preliminary orbital fitting software reported 3 consecutive errors indicating an anomalous trajectory. Dr. Marta Silva, the astronomer on duty, first noticed this anomaly flag. She manually reviewed observation frames from the preceding 3 nights and discovered the target was moving at an astonishing speed of approximately 245,000 kilometers per hour. More critically, its preliminary orbital eccentricity far exceeded 1, indicating it was not a known member of the solar system's celestial family. A clear signal suggested we might be facing an interstellar visitor. The Atlas telescope, formerly known as the Asteroid-Terrestrial Linus Impact Last Alert System, was primarily designed to provide early warning of near-Earth objects potentially threatening our planet. The system comprises 4 telescopes located in Hawaii, Chile, and South Africa, capable of scanning the entire observable sky multiple times every 24 hours. At its core is a telescope featuring a 1-meter primary mirror and a 100-megapixel CCD camera. This configuration enables it to detect objects 2.5 million times fainter than the human eye's limit. Automated software identifies moving targets by comparing consecutive images and submits potential threats to astronomers for manual review. Dr. Silva immediately recognized that A25X Joan did not match any known celestial body. She swiftly initiated emergency observation protocols, prioritizing tracking observations from the other 3 Atlas telescopes worldwide. Over the next 6 hours, the 4 telescopes collaboratively locked onto the target. Continuous observational data ruled out instrument malfunction or data errors. Orbital calculation confidence steadily increased with the growing data volume. Preliminary orbital solutions revealed an eccentricity exceeding 6. This unambiguously indicated a hyperbolic trajectory, confirming the object did not originate within our solar system. It traversed our home on an open curve with no return. This marks the first time in human history that an interstellar object has been detected while entering the inner solar system. Previous interstellar visitors, MUA and Borisov, were only discovered as they were about to depart. Dr. Silva immediately issued an alert through the International Astronomical Union's Minor Planet Center. This electronic bulletin, designated MPEC 2025-OS even, sent shockwaves through the global astronomical community. The bulletin contained preliminary orbital parameters and observational data for A25X Joan, confirming it as a suspected interstellar object. Over the next 24 hours, the global astronomical community launched an unprecedented collaborative effort. From the Keck telescope in Hawaii to the Very Large Telescope in Chile, from the Calais Alto telescope in Spain to the Palomar Observatory in the United States. 30-1 professional observatories across 6 continents joined the observation effort. By midnight on July 2, a total of 120 high-quality observational data sets had been compiled at the Minor Planet Center. Based on this data, astronomers were able to precisely calculate its orbit. The International Astronomical Union formally designated it as 3I Atlas. The 3I signifies the 3rd confirmed interstellar object. Atlas adopts the name of the telescope system that discovered it. The official naming signifies scientific confirmation of its interstellar origin. 3I Atlas becomes the 3rd confirmed visitor from beyond our solar system, following 1I MUA in 2017 and 2I Borisov in 2019. Unlike its predecessors, however, 3I Atlas was captured during its entry phase. This provided humanity with a valuable observation window spanning several months. Retrospective analysis following its official designation revealed an even more surprising fact. Amateur astronomer Sundin, while combing through Atlas telescope's archived data, discovered the system had actually detected 3I Atlas as early as June 25, but the automated classification system had mistakenly dismissed it as background noise. The reason was that the object happened to be transiting directly in front of the galactic center. The galactic center is the densest and brightest region of stars in the sky. This intense stellar background makes detecting faint moving objects exceptionally difficult. This coincidence allowed the interstellar visitor to remain hidden in plain sight for nearly a week. Astronomers refer to this concealment effect as galactic glare. The stellar density toward the galactic center is tens of thousands of times greater than that toward the North Pole. Every square arc-minute is packed with the light of countless distant stars. A faint, moving object is easily drowned out against such a backdrop. Unless its motion or brightness exhibits highly unusual characteristics, it remains difficult for algorithms to detect. The approach path chosen by 3I Atlas was almost a natural camouflage corridor. It cleverly utilized the densest and brightest region of our night sky as cover, only triggering alerts when it drew sufficiently close to the sun for its brightness to significantly increase. This discovery has sparked deep contemplation among scientists. Was 3I Atlas's approach direction a pure cosmic coincidence, or the result of some deliberate route planning? If the latter, its implications would overturn our understanding. Using the galactic center as cover to approach a planetary system sounds more like strategy than natural phenomenon. Natural celestial bodies move randomly and without purpose within the galaxy. Their orbital distributions should follow statistical patterns, not exhibit strategic characteristics. The first hint of unusual behavior began to emerge in 3I Atlas's trajectory. Continuous observations by the Global Observatory Network have also revealed another critical feature. Follow-up observations on July 2 reported faint coma activity, detected by multiple telescopes. A coma is the envelope of gas and dust formed when a comet heats up and vaporizes as it approaches the Sun. Observations from the Vera Rubin Observatory confirmed the presence of a diffuse coma around 3I Atlas. Its diameter is estimated at 15 miles, significantly larger than the estimated size of the nucleus itself. Simultaneously, the images revealed a potential tail structure, although its morphology differs from that of a typical cometary tail. Based on these observations, the Minor Planet Center formally classified it as an interstellar comet. The confirmation of cometary activity holds significant importance. It indicates solar radiation has begun affecting the surface of the subject. Volatile substances like water ice, carbon monoxide, and carbon dioxide are sublimating. This opens a window for spectral analysis of its chemical composition. By analyzing the spectrum of its coma, astronomers can identify constituent elements and molecules. This allows comparison with comets within the solar system to see chemical similarities and differences. These chemical fingerprints may reveal characteristics of the stellar environment where it was born. The discovery process of 3I Atlas itself marks a new era in astronomy. It demonstrates the formidable power of global telescope networks and automated sky and INS survey systems. The entire sequence from discovery to confirmation to global collaborative observation was completed within 48 hours. Such responsiveness would have been unimaginable a decade ago. It proves our near-Earth space monitoring capabilities have undergone a qualitative leap. We are not only capable of warning against threats originating within our solar system, but also equipped to capture fleeting interstellar messengers as they pass by. Yet amidst the excitement, astronomers harbor a lingering concern. Calculations confirm 3I Atlas's trajectory poses no threat to Earth, with its closest approach remaining approximately 1.7 billion miles away. Nevertheless, its immense size and high velocity remain striking. Were such an object heading directly toward Earth, our current technology offers virtually no effective means of defense. Its discovery reminds us that the cosmos is both wondrous and fraught with peril. As the first week of July passes, 3I Atlas steadily advances within the field of view of scientists' telescopes. Its steadily increasing brightness now allows observation by more medium-sized telescopes. Astronomy enthusiasts worldwide are also turning their lenses toward this distant visitor. Countless photographs and observational data are flooding into professional institutions. This is a cosmic observation feast with global participation. And this is only the beginning. More astonishing secrets about 3I Atlas are about to be unveiled in subsequent observations. Its trajectory, its composition, its age, each question stirs the hearts of scientists. Humanity stands at the threshold of a new era, gazing upon this messenger from the vast sea of stars, anticipating the cosmic messages it brings. After repeated calculations by observatories worldwide, 3I Atlas's orbital data is presented to scientists. Behind these cold numbers lies a startling physics puzzle. Its orbital eccentricity is precisely calculated at 6.14. This value far exceeds the 1-point error threshold defining interstellar objects. By comparison, Oumuamua, humanity's first discovered interstellar object, has an eccentricity of 1.0. The second, comet Borisov, has an eccentricity of 3.36. 3I Atlas's 6.14 signifies an extremely open hyperbolic orbit. Its trajectory bends only minimally under the Sun's gravitational pull, like a cosmic bullet fired into the solar system. It hurtles toward the Sun along a nearly straight path. This extreme orbital shape stems from its astonishing initial velocity. When 3I Atlas entered the Sun's gravitational influence from infinite distance, its heliostat velocity reached 68 kilometers per second. This speed far exceeds the orbital velocity of any natural body within the solar system, and even surpasses the Sun's orbital speed around the Milky Way. To grasp the sheer terror of this velocity, consider an intuitive comparison. The farthest spacecraft in human history, Voyager 1, reached a maximum speed of approximately 17 kilometers per second. Atlas 3I's velocity was over 4 times that of Voyager. Any modern chemical rocket-based interception mission would be utterly futile against such a high-speed object. Astronomers revealed the relative motion between Atlas 3I and Earth through precise calculations. Since Earth itself orbits the Sun at 30 kilometers per second, while the 3I Atlas entered the ecliptic plane at a near-minus vertical angle in retrograde motion, this resulted in a peak relative velocity of 98 kilometers per second between it and Earth, equivalent to 350,000 kilometers per hour. This figure shattered the speed record for any known object within the solar system. Such extreme relative velocity makes precise observation extremely challenging, akin to attempting to clearly photograph a supersonic bullet with a ground-based telescope. What further perplexes orbital dynamics experts is its retrograde orbit. 3I Atlas's orbital inclination was measured at 175 degrees. This means its direction of rotation is nearly completely opposite to that of all the planets in the solar system. Like a swimmer against the current, it races toward the Sun along a path opposite to the movement of the planetary family. During the solar system's formation, the vast majority of material rotated in the same direction. Thus, retrograde bodies are statistically extremely rare. The probability of a randomly entering interstellar object possessing such a high inclination is less than 2%. However, the true shock came from projections of 3I Atlas's future orbit. When scientists projected its orbital model into the solar system, an incredible coincidence emerged. Calculations revealed that over the coming months, make unusually close encounters with multiple planets within the solar system. It will pass within 0.65 astronomical units of Venus, then fly by Mars at a distance of 0.19 astronomical units, and finally complete its closest planetary encounter near Jupiter at 0.36 astronomical units. The precision of each approach is unsettlingly exact. Statisticians swiftly calculated the probability of such multiple planetary close encounters, given an interstellar object randomly entering the solar system, with entirely random orbital parameters and arrival time. The probability of such precisely aligned multiple encounters is merely 0.05%, a probability so low it would raise suspicion in any rigorous scientist. Either humanity is witnessing the most incredible coincidence in solar system history, or this object's orbit is not entirely the product of natural randomness. 3I Atlas's orbital design appears meticulously calculated. It ingeniously utilizes planetary gravitational fields for subtle orbital adjustments. This technique, known as the gravity slingshot effect, is a common energy-saving orbital design method for human deep-space probes. Yet the sophistication of the slingshot sequence demonstrated by 3I Atlas far surpasses any human orbital design mission. It appears to maximize the observational opportunities offered by planetary gravitational fields during a single transit through the solar system. Another astonishing discovery in orbital calculations concerns its Hurtling timing. 3I Atlas will reach its closest point to the Sun on October 29, 2025, at a distance of approximately 1.36 astronomical units, positioned precisely between the orbits of Earth and Mars. The critical issue is that from Earth's perspective, the object will be almost entirely obscured by the Sun's glare. It will remain hidden behind the Sun for a full 3 months, during which no optical telescope on Earth will be able to observe it. This eject's window holds particular significance in orbital mechanics. The vicinity of Hurtling is the optimal location for executing what is known as the Oberth effect maneuver. A spacecraft applying thrust here achieves maximum energy minus change efficiency. Should 3I Atlas require deceleration to achieve capture by the solar system, or perform significant orbital corrections, this period of solar occultation presents the ideal window for action. Any such activity could be conducted entirely beyond Earth's observational reach. This serendipitous timing has sparked intense debate within the scientific community. Harvard astrophysicist Avi Loeb has publicly argued that such a combination of orbital characteristics is statistically improbable to occur naturally. A randomly moving interstellar object, entering the solar system on a retrograde orbit, encountering multiple planets at close range, while coincidentally remaining in Earth's observational blind spot during the most critical dynamic period. The probability of these coincidences occurring simultaneously approaches zero. However, the mainstream astronomical community remains cautious. Dr. Chris Lintert points out that the universe is filled with low-minus probability events. The reason we observe these coincidences is precisely because we, as observers, exist within this specific space-time. This is known as the selection effect, or anthropic principle. We should not readily equate statistical anomalies with intelligent design. To understand how 3I Atlas attained such astonishing velocity, scientists retraced its possible path through the Milky Way by computer-simulating its motion over hundreds of millions of years, revealing it likely underwent multiple close encounters with stars. Each gravitational assist acted like a cosmic slingshot, gradually accelerating this interstellar projectile to the velocity we observe today. Its lengthy journey through the galactic thick disk accumulated unimaginable kinetic energy. The Enigma 3I Atlas's trajectory compels humanity to rethink the laws governing interstellar motion. It may simply be an exceedingly rare natural wonder, a cosmic slingshot perfectly accelerated through the Milky Way's gravitational field, or it could represent some cosmic phenomenon we have yet to comprehend. It might even challenge our understanding of the boundary between nature and artifice. As it continues its advance toward the inner solar system, further observational data may offer clues to its origins. Yet even now, its flight path itself stands as one of the most captivating enigmas in astronomical history. As global telescope arrays maintain their focus on 3I Atlas, preliminary measurements of its physical characteristics begin to emerge. What astonishes astronomers most is its estimated colossal size. Conservative calculations based on its brightness and albedo suggest its core diameter could reach 20 kilometers. This figure dwarfs the scale of all previously known interstellar objects. MUA, discovered in 2017, measured only about 400 meters at its longest dimension. Comet Borisov, observed in 2019, had a nucleus diameter of approximately 1 kilometer. Yet 3I Atlas is over 50 times larger than MUA and 20 times larger than Borisov. It is no longer an insignificant interstellar fragment, but an interstellar behemoth. This scale severely challenges current models of interstellar object formation and distribution. Theoretical astrophysicists have long held that fragments ejected from stellar systems typically measure on the kilometer or sub-kilometer scale. A 20-kilometer- class object requires an extremely violent stellar system disturbance event, such as a close stellar encounter or major instability in a protoplanetary disk, to gain sufficient escape velocity from its parent system. The existence of 3I Atlas suggests that such massive interstellar wanderers may be more common in the Milky Way than previously thought, or that we have witnessed an exceptionally rare cosmic ejection event. The Vera Rubin Observatory provided more precise measurements through its advanced optical systems. Its data indicates 3I Atlas's solid nucleus has a diameter of approximately 11.2 kilometers. However, its total visible extent, including its faint coma, extends to 15 miles. This size surpasses many known mass belt asteroids, making it the largest interstellar object ever observed within the solar system. Its immense mass confers greater inertia. Solar radiation pressure exerts negligible influence on its orbital path. This also explains why its hyperbolic trajectory remains so remarkably stable. Yet its size anomaly is merely the first peculiarity presented by 3I Atlas. More perplexing is its anomalous cometary behavior despite lacking typical cometary activity. Though officially classified as an interstellar comet, 3I Atlas remained unusually silent during its solar approach. It failed to display typical cometary features like a bright coma or distinct ion tail. Multiple observation teams reported detecting only an extremely faint coma in early July. Its surface outgassing activity was far below expectations for a solar system comet of comparable size. Dr. Alan Hale explicitly noted in his July 2 observation record, the target lacks visible coma structure, inconsistent with typical cometary characteristics. Its surface albedo distribution is uniform, showing no significant jets or plumes. This low activity level persisted for nearly a week, until mid-July when the coma became relatively prominent and detectable. Yet this activity level remained far below predictions based on its size and distance from the Sun. What baffled cometary experts most was the anomalous behavior of its dust tail. Observations by the Vera Rubin Observatory team in late July revealed that 3I Atlas did indeed possess a detectable dust tail structure. However, the tail's orientation completely defied known comet physics. Typically, a comet's dust tail is pushed away from the Sun by solar radiation pressure, forming the characteristic structure extending away from the Sun. Yet 3I Atlas's dust tail exhibited an anomalous angle pointing toward the Sun, as if material were being actively ejected toward the Sun. The only plausible explanation for this anomaly is that 3I Atlas is ejecting exceptionally heavy, massive dust particles. These particles may reach millimeter or even centimeter scales. Their mass too great for solar radiation pressure to effectively push them away. Consequently, these ejecta form a sunward pointing tail structure under solar gravitational influence. Calculations indicate that the particle mass required to produce this effect is thousands of times greater than typical cometary dust particles. Mass loss rate calculations further deepen this mystery. Researchers estimate 3I Atlas's outgassing rate to be between 0.1 and 1 kg per second. This rate is nearly negligible for a 20-kilometer- class comet, equivalent to losing less than 1/10 billionth of its total mass every millennium. This extremely low mass loss rate contradicts its visible coma activity, suggesting its outgassing mechanism may differ from traditional ice sublimation processes. Spectral analysis adds a new dimension to this puzzle. When large telescope spectrometers targeted comet 3I Atlas's coma, scientists expected to observe familiar spectral features of water ice and carbon monoxide. Yet preliminary spectral data reveal an unusual combination of absorption and emission lines. These spectral patterns cannot be fully matched to the typical chemical composition of solar system comets. Some faint spectral features may point to silicates and metal oxides, but the signal minus-to-minus noise ratio is too low for definitive identification. More striking are its visible minus-light reflectance spectral characteristics. 3I Atlas exhibits unusual color variations in the visible spectrum. Its surface reflectivity changes with wavelength in a SO- called rainbow effect. This phenomenon is typically associated with complex surface compositions or structures. It may correlate with metallic surface oxides or specific mineralogical features. Such spectral diversity is quite rare in natural celestial bodies. However, it bears some similarity to spectral features observed on artificial satellites or rocket upper stages. Measurements of its surface albedo also yielded unexpected results. The overall geometric albedo of 3I Atlas is estimated between 0.04 and 0.06. This is slightly higher than typical cometary nuclei but far below the reflectivity expected from metallic surfaces. However, its surface reflectivity distribution is unusually uniform. It shows none of the typical bright-dark variations or mottled structures common on comets or asteroids. This uniformity may suggest it has undergone long-term space weathering, or an unusually homogeneous internal structure. Measuring the core's rotation period also proved challenging. Despite intensive photometric observations, astronomers failed to detect any significant periodic brightness variations. This implies that 3I Atlas either possesses an extremely long rotation period, or its rotational axis is precisely aligned with Earth, making brightness changes imperceptible, or its surface reflectivity distribution is indeed exceptionally uniform. Whichever scenario holds true, it heightens the object's unusual nature as a natural celestial body. All these anomalous features combined paint a cosmic object, defying simple classification. It is too massive to fit typical interstellar debris models. It is too quiet, lacking expected cometary activity. Its dust gel points in the wrong direction, violating fundamental physics. Its spectral characteristics are both familiar and unfamiliar. Its surface uniformity is suspiciously even. These traits collectively form a coherent puzzle, challenging every assumption held by astronomers. A division is emerging within the scientific community. One faction believes we are witnessing an entirely new class of celestial object, an interstellar body forged in extreme cosmic conditions, whose properties reflect states of matter or formation mechanisms we have yet to comprehend. Another faction is seriously considering more radical possibilities. Perhaps Comet 3I Atlas's peculiarity stems from its non-natural origin. Perhaps what we are observing is not an ordinary comet or asteroid, but some kind of artificial object with technological features. As 3I Atlas continues its journey inward toward the inner solar system, further observational data may resolve these questions. Yet even now, its physical properties alone have become the most captivating subject in solar system astronomy. Each new discovery seems to deepen rather than dispel the mystery surrounding it. This interstellar visitor is compelling humanity to rethink the diversity of material forms we might encounter in the cosmos. Determining 3I Atlas's interstellar origin is merely the first step in scientific exploration. A deeper question immediately confronts astronomers. From where in the Milky Way did this interstellar visitor originate? And how long has it drifted through the cosmos? Answering these questions requires tracing its lengthy path through the galaxy. It's akin to observing a bullet's instantaneous flight and attempting to reconstruct its entire history of production, transport, and launch. The answer lies hidden within 3I Atlas's precisely measured 3-dimensional velocity vector. When scientists decomposed its velocity into 3 components relative to the galactic coordinate system, a startling pattern began to emerge. Its vertical velocity component reached an astonishing 185 kilometers per second. This value far exceeds the motion of most stars near the Sun. In galactic dynamics, vertical velocity serves as a key indicator for distinguishing stellar populations. Our Sun belongs to the thin disk population, with a vertical velocity of merely 7 km, while 3I Atlas's high vertical velocity unequivocally places it within the thick disk population. The Milky Way's disk structure actually comprises 2 distinct components. The thin disk represents the galaxy's most active star-forming region, hosting abundant young stars and rich heavy elements, whereas the thick disk constitutes an older, sparser stellar population. Their stellar ages typically exceed 8 billion years and can reach up to 13 billion years. Thick disk stars form during the turbulent early stages of the Milky Way, when the galaxy was larger in scale and more loosely structured. These ancient stars have witnessed the entire evolutionary history of the Milky Way. A team led by Matthew Hopkins at the University of Oxford utilized the latest galactic dynamical model to conduct millions of computer simulations of 3I Atlas's orbit. Their analysis indicates a 68% confidence level that the object's age falls between 7.6 billion and 14 billion years. The lower limit of this age range far exceeds the ages of Earth and the Sun. while the upper limit approaches the universe's own age of 13.8 billion years. If this estimate proves accurate, 3I Atlas could be the oldest material directly observed by human science. The key evidence for this age estimation stems from its dynamical association with thick disk stellar populations. Thick disk objects bear specific chemical signatures, typically exhibiting low metallicity, indicating a scarcity of heavy elements in the interstellar medium from which they formed. This aligns with the early evolutionary history of stars in the universe. First-generation stars were composed almost entirely of hydrogen and helium. They produced the first heavy elements through nucleus synthesis. Subsequent supernovae explosions dispersed these elements into the interstellar medium. Later forming stars thus contained progressively increasing heavy elements. If 3I Atlas indeed formed within a thick disk environment, its internal composition should exhibit low metallicity. This prediction provides a critical test for forthcoming spectroscopy analysis. Should the spectrum confirm significantly lower metallicity than solar system comets, it would strongly support the thick disk origin hypothesis. Contrary results may necessitate re-evaluating its formation history. Throughout the Milky Way's long history, 3I Atlas may have encountered countless stars. Each close encounter with a star acted like a gravitational slingshot, slightly altering its orbit and increasing its kinetic energy. After billions of years of cumulative effects, these random encounters ultimately shape the astonishing velocity we observe today. Its speed functions like a cosmic odometer, recording the vast distances it has traversed within the galaxy. Computer simulations suggest 3I Atlas may have originated in the outer regions of the Milky Way's thick disk, where stellar density is lower and the interstellar environment more tranquil. Its primordial home likely orbited an ancient, metal-poor star, which may have long since ended its life cycle. As a white dwarf neutron star, or even a black hole, its planetary system was likely destroyed during the star's evolution. This makes tracing 3I Atlas's exact origin nearly impossible. Another thought-provoking possibility is that 3I Atlas may not have formed within a specific stellar system. It instead condensed directly from the interstellar medium. During the early, denser interstellar medium phase of the Milky Way, theoretically, planetary mass objects could condense directly from gas clouds. Although this formation mechanism remains unproven, certain characteristics of 3I Atlas align with this hypothesis. If 3I Atlas truly possesses an age approaching the age of the universe, it may carry direct information about the Milky Way's earliest stages. Its chemical composition may record traces of first-generation stellar nucleus synthesis. Its surface may preserve environmental characteristics from the galaxy's first hundreds of millions of years. It functions like a cosmic time capsule, sealing precious memories from the Milky Way's infancy. Given its potentially extreme age, 3I Atlas may have witnessed multiple pivotal evolutionary phases of the Milky Way. It likely experienced numerous mergers between the Milky Way and dwarf galaxies, observed the transition of the Milky Way's thick disk to a thin disk, or witnessed the formation and evolution of the galaxy's spiral arm structure. Its trajectory may encode the evolutionary history of the Milky Way's gravitational potential. Comprehending such temescals from the perspective of Earth's life is nearly impossible. When Earth began forming 4.6 billion years ago, 3I Atlas may have already been drifting through the Milky Way for 9 billion years. When the earliest life emerged on Earth, it continued its silent journey through interstellar space. When dinosaurs ruled the planet, it remained on its voyage. As human civilization began to sprout, it gradually approached the solar system. This temescal transcends the grasp of human intuition. 3I Atlas's thick disk origin also explains its anomalous motion direction. Thick disk objects typically exhibit high orbital inclinations and eccentricities. This perfectly aligns with 3I Atlas's observed retrograde, highly inclined orbit. Its kinematic characteristics fully match statistical expectations for thick disk objects. From the perspective of galactic dynamics, 3I Atlas's behavior is actually quite normal. What is unusual is our opportunity to observe a thick disk object at such close range. If 3I Atlas is indeed a thick disk object, its discovery carries profound implications. It suggests that the oldest material in the Milky Way, may frequently traverse our young solar system. We inhabit a crossroads where different stellar populations of the galaxy intersect. Young objects from the thin disk meet ancient ones from the thick disk here. Predictions from the Vera Rubin Observatory indicate we may discover dozens of similar interstellar visitors over the next decade. Some may similarly originate from the thick disk population. This will open new windows into studying the early history of the Milky Way. 3I Atlas may be just the tip of the iceberg, representing a vast and ancient population of interstellar objects. From the grand perspective of cosmic evolution, 3I Atlas's approach is a meeting across time. What we observe through our telescopes is not merely a distant visitor in space, but an ancient messenger from time. It brings not only a material sample from interstellar space, but direct evidence of the universe's infancy. When 3I Atlas reaches its closest approach to the Sun, humanity will have a fleeting opportunity to study this cosmic relic before it resumes its endless galactic journey, possibly traveling billions of years more, until captured by some star system, or drifting eternally through interstellar space. Our solar system is merely a brief interlude in its long voyage, yet it offers humanity a precious window into the deepest history of the cosmos. Within 3 hours of confirming 3I Atlas as an interstellar object, the SETI Institute's emergency response protocol was activated. Director Drive, and you see my unauthorized the highest -level monitoring protocol. This decision stemmed from a simple yet profound question. If this interstellar visitor is not a natural celestial body, do we possess the capability to identify its potential technological signatures? The Allen telescope array completed observational mode reconfiguration within 7 hours, commencing round the clock, uninterrupted monitoring of 3I Atlas. SETI Institute's monitoring strategy is built upon decades of theoretical groundwork. Scientists systematically mapped potential pathways for detecting technological signatures. The primary objective was to search for narrowband radio signals virtually impossible to generate naturally in the cosmos, and among the clearest indicators distinguishing artificial from natural sources. The monitoring frequency range covered the microwave window from 1 to 10 GHz. This band experiences relatively minimal attenuation when propagating through interstellar medium, and is considered a potential interstellar communication frequency band. The second key monitoring target is broadband radar signals, resembling the characteristics of Earth-based military radar or interplanetary radar. Such signals could be employed for navigation or topographic mapping, particularly if 3I Atlas requires orbital corrections or environmental sensing. Signal feature analysis includes pulse repetition frequency modulation schemes and polarization characteristics. These technical parameters may reveal the potential purpose and technological sophistication of the signal source. The monitoring team also focuses specifically on potential optical laser signals, short-pulse laser communications in the visible or near-infrared bands. This communication method offers advantages of high directionality and energy concentration. While atmospheric turbulence may affect signal quality, laser communication holds significant advantages in the vacuum of space. Automated systems can thousands of optical frequency channels per second to detect any non-natural spectral emission lines. Beyond active signal searches, SETI scientists also monitor passive signatures, including anomalous thermal distribution patterns on object surfaces. Natural celestial bodies typically exhibit thermal radiation consistent with black-void radiation loss. Objects harboring internal energy sources or technological activity may display anomalous temperature distributions or spectral characteristics. Observations in the mid-infrared band, in particular, may reveal the presence of waste heat. The Allen telescope array generates unprecedented volumes of monitoring data, accumulating 21 terabytes within its first week of operation. This data volume equates to tens of thousands of hours of continuous high-definition video recording. Analyzing such an ocean of data requires cutting-edge computational technology. The SETI Institute deployed newly developed artificial intelligence systems, employing deep learning algorithms for preliminary signal screening. The signal processing workflow involves multiple complex steps. First, radio frequency interference is identified and filtered out. Millions of terrestrial radio sources exist, including broadcast, television, satellite communications, and ground-based radar. These signals interfere with the detection of extraterrestrial signals. Through multi-anoscope observations and signal feature comparisons, the system effectively identifies and eliminates the vast majority of ground-based interference. Candidate signals passing initial screening advance to detailed analysis. Scientists examine their frequency stability, modulation complexity, and whether they contain mathematical structures or repetitive patterns. These features may suggest intelligent design. Particularly noteworthy are signals whose frequency drift aligns with the 3i atlas, relative to Earth's Doppler effect. Within the first month of monitoring, the system identified 17 secondary candidate signals. These signals pass preliminary RF interference filtering. However, in-depth analysis confirmed all were natural phenomena, or unknown side lobe radiation from human technological activities. No conclusive evidence was found indicating 3i atlas is emitting detectable artificial signals, yet radio silence does not rule out technological existence. SETI Chief Scientist Drive Natasha Bhattacharya noted that advanced civilizations may communicate using physical principles unknown to us, or employ highly directional transmission methods to avoid energy waste. They might also actively maintain radio silence and adherence to the dark forest principle. Monitoring aligns more closely with prudent interstellar conduct than broadcasting. Beyond traditional SETI methods, the monitoring team explored innovative approaches. They analyzed whether 3i atlas's light curve exhibited regular brightness variations, potentially representing encoded information. This technique resembles Earth's optical communications satellites, but transmits data by modulating the reflected light intensity of an entire celestial body. Preliminary analysis detected no patterns exceeding natural statistical fluctuations. Another intriguing research direction involves analyzing the composition of the dust trail. If 3i atlas is an artificial object, its emissions may contain unnatural chemical substances or isotope ratios, such as fission products or elements characteristic of industrial processes. Although current spectral resolution is limited, follow-up observations may utilize the James Webb Space Telescope for more detailed analysis. The SETI Institute also collaborates with space situational awareness networks to monitor for smaller companion objects around 3i atlas. These could be detached probes or communication relays. Using adaptive optics and laser ranging techniques, scientists attempt to detect any anomalous light points or motion patterns. To date, no definitive evidence of companions has been found. Parallel to monitoring efforts, ethical debates persist. Should humanity respond if artificial signals are indeed detected? The International Union of Academies convened an emergency workshop to discuss protocols and potential risks of interstellar communication. Mainstream opinion favors caution until signal nature is confirmed, avoiding immediate replies to prevent potential adverse consequences. However, some scientists advocate a more proactive engagement strategy. A research team led by Professor Ove Lowe proposes that if 3i atlas exhibits anomalous behavior near its perihana, sending simple mathematical sequences or friendly greetings should be considered. They argue that missing the first contact opportunity carries its own risks. Encounters between technologically advanced civilizations in the cosmos may be once lifetime events. Another crucial aspect of the monitoring mission is international collaboration. China's 5-100-meter aperture spherical radio telescope FAST and Europe's low-frequency array LFA have joined the monitoring network. This global cooperation significantly enhances signal detection sensitivity and interference identification reliability, embodying the borderless nature of science. As 3i atlas continues its journey into the inner solar system, monitoring strategies are being continuously adjusted and optimized. Scientists pay particular attention to the timing of critical orbital events, such as planetary close encounters and perihana transits. These moments are most likely to trigger any pre-set automated systems. The SETI Institute regularly publishes progress reports on monitoring activities. All data is made publicly available to the scientific community after preliminary analysis. This transparency aligns with the spirit of science, while preventing unnecessary speculation and rumor propagation. The Daily Minus updated website serves as a window for the public to follow search progress on a scientific level, regardless of the monitoring results. This concentrated search campaign holds significant value. It tests the rapid response capabilities of the global SETI community, validates the latest signal processing algorithms and hardware systems, and accumulates invaluable experience for potential future direct contact. The approach of 3i Atlas presents a unique opportunity to test various hypotheses and detection methods regarding extraterrestrial technology, even if it ultimately proves to be just another natural phenomenon. The technological and experiential advancements gained from this comprehensive monitoring will also lay the groundwork for humanity's future interstellar exploration. As this interstellar visitor eventually departs the solar system, SETI monitoring will persist until the signal fades beyond detection. Scientists recognize that the next cosmic encounter remains unpredictable, thus demanding full utilization of this precious opportunity to listen for the potential voice of intelligence amidst the infinite cosmic silence. As the anomalous characteristics of 3i Atlas continue to accumulate, the scientific community has begun seriously considering the possibility of its non-natural origin. Professor Avi Loeb, former director of Harvard's Department of Astronomy, was the first to speak out. He published a paper in Science that caused a sensation, systematically presenting the view that 3i Atlas may represent extraterrestrial technology. His paper quickly transcended the realm of academic discussion, sparking global scientific debate and public imagination. Loeb's argument rests upon 5 key anomalous characteristics. The first and most intuitive feature is the object's immense size. An interstellar object measuring 20 kilometers in diameter is statistically extremely rare, based on current models of planetary system formation and ejection mechanisms. The probability of such a massive celestial body being expelled from its parent system is minuscule. Loeb calculated the probability of randomly discovering an interstellar object of this size to be less than once per millennium. The second pivotal argument concerns its exceptionally precise orbital geometry. The sequence of close encounters between 3i Atlas and multiple planets is mathematically improbable as pure coincidence. Loeb's team demonstrated through Monte Carlo simulations that the random occurrence probability of such multiple approaches is approximately 0.005%. When accounting for the precise temporal synchronization of these encounters, the probability further diminishes to the 1 minus n minus a minus million range. The third argument centers on its anomalous cometary activity, particularly the peculiar behavior of its dust tail pointing toward the sun. Loeb noted this aligns with the characteristics of directed material ejection, rather than the sublimation process caused by passive solar heating. Natural comets' dust tails always point away from the sun, a fundamental physical law governed by radiation pressure. Yet 3i Atlas's behavior clearly defies this principle. The fourth anomaly lies in the uniformity of its spectral characteristics. Natural celestial bodies typically exhibit complex spectral diversity, reflecting their heterogeneous surface composition and geological history. Yet Comet 3i Atlas displays an unusually uniform spectrum, suggesting it may be composed of engineered materials or have undergone an extreme homogenization process. The fifth and most contentious argument concerns its perfect timing during the solar eclipse window. Loeb contends this provides optimal cover for any technological activity. If intelligent control exists, this would be the ideal moment to execute critical operations. Such coincidental timing is difficult to explain as mere coincidence. Based on these anomalies, Loeb proposes 3 possible technological hypotheses. The first hypothesis posits that 3i Atlas is an autonomous interstellar probe, specifically engineered to survey a systems harboring planets, with an orbital design optimized for scientific yield, to observe multiple potentially habitable worlds during a single transit. The second hypothesis posits it as a generational spacecraft or cosmic ark, whose immense dimensions could accommodate a complete ecosystem, or a civilization's cryogenic embryo repository. This explanation accounts for its anomalously massive mass, and the compact structure implied by its relatively low outgassing rate. The third and most radical hypothesis is that 3I Atlas is a von Neumann probe, a self-replicating interstellar robot, whose immense size provides sufficient material resources to construct replicas within the target star system. This hypothesis explains the necessity for such a colossal structure. Lieb's paper immediately drew strong reactions from the mainstream astronomical community. Professor Edward Bloom, an astrophysicist at the California Institute of Technology, published a rebuttal in Nature, highlighting Lieb's selective use of evidence. Bloom emphasized that anomalous data itself does not constitute evidence of artificial origin, but rather reflects gaps in our understanding of interstellar astrophysics. Bloom systematically addressed Lieb's 5 main arguments. Regarding size, he noted the influence of observational selection effects, making large interstellar objects easier to detect than smaller debris. Current observational capabilities favor detecting massive bodies like 3I Atlas. The statistical probability calculations require correction for this bias. Regarding orbital coincidence, Bloom introduced new dynamical simulations, showing that within specific orbital families of thick-disk objects in the Milky Way, the probability of multiple planetary encounters is actually significantly higher. 3I Atlas's peculiar orbit may reflect its thick-disk origin, rather than intelligent design, for the anomalous dust-tail direction. Bloom proposes a novel physical explanation involving complex interactions between super-large dust particles and the solar magnetic field under extreme size and velocity conditions. Known cometary physics may require revision. Spectral uniformity can be explained by the homogenizing effect of long-term space weathering. An object traveling through interstellar space for billions of years may have its surface abraded to exceptional uniformity. This is not evidence of artificial fabrication, but a sign of ancient age. Regarding the coincidental timing of the eclipse window, Bloom points out this is a classic example of observer bias. We notice this coincidence only because we are observers. Had 3I Atlas arrived at any other time, we would never have noticed this so-called anomaly. Amid this intense scientific debate, a third voice began gaining attention. MIT professor Sarah Chen proposed a middle ground. She posits 3I Atlas may be a modified natural body. An advanced civilization may have utilized a pre-existing asteroid or comet nucleus and engineered it to meet interstellar travel requirements. This hypothesis acknowledges its natural origins while accommodating the possibility of technological modification. Chen's hypothesis receives indirect support from observational data. 3I Atlas exhibits both natural and anomalous surface features. Certain spectral regions align with typical cometary composition, while others display unnatural uniformity. This may reflect traces of partial engineering modifications. Monitoring data from the SETI Institute also offers fresh perspectives to this debate. Although no explicit artificial signals have been detected, certain faint radio emission patterns have aroused interest. These signals are too weak to confirm a technological source, yet they differ from known natural radio phenomena. This ambiguity precisely reflects the current dilemma. Psychological and sociological factors are now entering the discussion. Throughout human history, natural phenomena have repeatedly been misinterpreted as artificial constructs. From Martian canals to the little green man hypothesis about pulsars, we tend to perceive patterns and schemas in ambiguous data. This tendency intensifies when confronted with the unknown. Simultaneously, another profound question emerges. If 3I Atlas is indeed an artificial artifact, why has it maintained such complete silence? No proactive communication, no orbital adjustments, no display of obvious technological features. This extremely conservative behavioral pattern may be related to the so-called dark forest hypothesis. The dark forest hypothesis was proposed by science fiction writer Lee C.I. Exon, but has been taken seriously by some astrobiologists. This hypothesis posits that civilizations across the universe maintain silence out of a rational fear of potential threats. Any civilization that reveals its location risks preemptive strikes from others. Within this framework, 3i Atlas's silence may reflect its creator's extreme caution, or indicate it was designed as a pure observer, strictly avoiding all interaction with target civilizations. Another possibility is that we are encountering relic technology, an ancient probe that ceased operation and drifted through interstellar space for millions of years before accidentally entering our solar system. This hypothesis explains its silence and lack of discernible activity. An unsettling variant hypothesis exists. 3i Atlas could be the final relic of an extinct civilization, a cosmic-scale time capsule, carrying the entirety of a vanished civilization's knowledge, or, more darkly, the cause of its extinction. Confronted by these competing theories, the scientific community is devising critical discrimination experiments. The upcoming Perilhana is viewed as a decisive moment. Should 3i Atlas perform an orbital correction behind the Sun that would constitute near-conclusive evidence of artificial origin, further refinement of spectral analysis is also underway to identify potential signatures of artificial materials, such as specific metal alloys or composite markers, which could provide the clearest evidence of technological signatures. Simultaneously, observation teams intensify the search for any micro-satellite objects an advanced probe might have released. These smaller objects are harder to detect but not impossible. Using the most advanced adaptive optics systems, astronomers are scanning the space around 3i Atlas. The only consensus in this great debate is 3i Atlas forces us to confront the limits of science. In the face of insufficient data, balancing open-mindedness with rigorous standards becomes a personal challenge for every researcher. Lieb summarized this dilemma in a recent interview. The essence of science is not to ensure we are correct, but to ensure we do not miss facts that could change paradigms. Whatever 3i Atlas ultimately proves to be, it has already fulfilled its scientific purpose, forcing humanity to expand its imagination of cosmic possibilities. As this interstellar visitor continues its journey through the inner solar system, answers may lie just ahead, but at this very moment, on the border between evidence and conjecture, science faces its most severe test. At the edge of the unknown abyss, human intellect engages in a silent dialogue with cosmic mysteries. On November 16, 1974, the Arispa radio telescope in Puerto Rico completed an unprecedented transmission. This 305-meter diameter radio telescope, then the world's largest, sent a meticulously encoded message toward the direction of the globular cluster N13 in the constellation Hercules. Known as the Arispa message, the signal lasted 116 seconds. It comprised 1679 binary encoded digits. This number represents the product of 23 and 73, signifying the dimensionality of the message matrix. Designed jointly by Frank Drake and Carl Sagan, the content included binary representations of numbers 1 through 10, the atomic numbers of elements found in DNA, chemical formulas of nucleotides, the double helix structure of DNA, an image of a human figure and average height, a map of planetary distribution within the solar system, and a schematic diagram of the Arispa telescope itself. This transmission held greater symbolic significance, as the N13 globular cluster lies 25,000 light-years from Earth. The message would take 25,000 years to reach its destination, and any response would require another 25,000 years to return. This pioneering endeavor established the fundamental template for human interstellar communication, employing mathematics and fundamental science as a universal language to showcase our biological characteristics and technological capabilities, marking our position in the cosmos. This template influenced all subsequent human attempts at interstellar communication. Following the Arispa message, humanity conducted multiple deliberate interstellar broadcasts. The Voyager 1-2 probes launched in 1977. Each carried a gold-plated copper disc. These discs are known as the Voyager Golden Records. Their content far surpasses the Arispa message in richness. The Golden Records contain 115 encoding images, natural sounds from Earth, including wind, rain, thunder, ocean waves, and animal calls. Greetings in 55 human languages, along with 27 musical pieces from diverse cultures and eras. Also included are greetings from then UN Secretary General Kurt Waldheim and a written message from U.S. President Jimmy Carter. The record sleeve features detailed playback instructions and a map of the solar system's location using symbolic language based on the relative positions of pulsars and hydrogen atoms, hyperfine transitions. These designs embody profound thoughtfulness in preserving human knowledge, so that even discoverers with no shared biological basis might still decode this information. Compared to these deliberate interstellar messages, Earth's unconscious radio emissions are far more widespread. Since we can achieve transatlantic radio transmission in the early 20th century, humankind has been inadvertently broadcasting our existence to the cosmos. Early radio broadcast signals were relatively weak, but the post-World War II proliferation of television technology and large scale deployment of radar systems significantly amplified Earth's radio radiation signature. These signals propagate outward at the speed of light, forming a sphere of signals approximately 200 light-years in radius. These unintentional signals exhibit varying characteristics. Early amplitude-modulated broadcast signals tend to attenuate relatively easily at interstellar distances. However, military radar and television broadcast relay satellite signals possess greater directionality and power, and may be detectable over much greater distances. Earth's radio signature peaked in the 1970s. Subsequently, with the proliferation of fiber-optic communications in satellite television, ground-based radio leakage has actually decreased. Yet Earth remains a conspicuous radio powerhouse for observers equipped with sufficiently sensitive technology. This unintentional broadcasting raises a profound question. If the 3i Atlas is indeed of artificial origin, it may have been drawn by Earth's radio signals. During its long galactic journey, it could have traversed our expanding radiosphere and adjusted course to investigate the signal's source. This hypothesis aligns with temporal coincidences in 3i Atlas's trajectory. Its arrival timing exhibits a mathematical consistency with the propagation range of Earth's radio signals. If it detected our presence at the edge of the signal sphere and approached at the observed velocity, the timing would indeed coincide. More thought-provoking is the recent communication anomaly of Voyager 1. This human probe, now in interstellar space, began transmitting garbled data around the time 3i Atlas was discovered. Though engineers found partial explanations for the issues, the temporal coincidence remains unsettling. Voyager 1 currently orbits over 24 billion kilometers from Earth, making it humanity's most distant man-made object. Its golden record may serve as civilization's final testament. Should human civilization someday vanish, Voyager and its carried information will continue drifting through the Milky Way, potentially preserved for billions of years. Now, the 3i Atlas is approaching from interstellar space, moving directly toward Voyager. Two messengers from different worlds are briefly encountering each other on the cosmic scale. The probability of such a meeting is extremely low, yet it is happening. This raises a fundamental philosophical question. Should we actively communicate with potential interstellar visitors? The scientific community is deeply divided on this issue. Supporters argue it is a once-lifetime opportunity, potentially establishing contact with another intelligent civilization. Opponents invoke the dark forest hypothesis, arguing that silence is the path to survival. The dark forest hypothesis posits that civilizations across the cosmos remain silent because any civilization revealing its location risks annihilation by more powerful ones. Under this perspective, humanity's radio transmissions of the past century may have committed a fatal error. The approach of 3i Atlas puts this theory to the test. If it truly originates from an advanced civilization, its behavioral patterns will reveal the true nature of interstellar politics in our galaxy, whether it's a cooperative community or a threatening dark forest. Meanwhile, a new interstellar communication project is underway. The Galactic Lighthouse initiative aims to transmit more complex messages containing mathematical, physical, biological, and sociological data about human civilization. This transmission will utilize multiple frequencies and sophisticated encoding to maximize interpretably. These endeavors reflect a deep seated human yearning to seek companionship in cosmic solitude, to confirm we are not the only intelligent beings. Even in the face of potential risks, we choose to make our voice heard. Now, as 3i Atlas silently navigates toward the inner solar system, it has become a mirror of human civilization, reflecting our hopes and fears, our courage and caution, our past and future. From ISPO to Voyager, from accidental leaks to deliberate messages, humanity has declared our existence to the cosmos, and now the universe may be responding. Whatever the nature of 3i Atlas, it has forever altered humanity's understanding of our place. We are no longer mere observers, but participants in the cosmic dialogue. In this grand cosmic narrative, humanity has only just begun writing its chapter, and 3i Atlas may be the first distant reply we have received.